Question 4. The product of a reaction is a red solution due to compound X, which is not the only product of the reaction. In order to study this reaction, solutions of X of different concentrations were examined spectrophotometrically. Part A. At what approximately wavelength would X absorb most strongly? For compound X to be red, it must absorb all of the wavelengths of light. If we look at the visible light part of the spectrum, we can see that it's red above 600 nanometers, which means compound X absorbs wavelengths below 600 nanometers. A stock solution that is 0.05 molar in X was used for their dilutions as follows. Buffer to stabilise pH. Calculate the concentrations of X for each solution. So for this question, we need to use the equation C1V1 equals C2V2, with the C1 being the concentration of the X, the V1 being the volume that was used, C2 is what we're calculating, and V2 is the volume of all of them put together. So for solution 1, our equation would look like this. 0.05 times 2 equals C2 times 2 plus 6 plus 2, which is just 10. So to rearrange to get C2, we get C2 equals 0.05 times 2 over 10, which is equal to 0.01. So if we do the same for all the other equations, we get 0.02, 0.025 and 0.03. Part C. The absorbance of each solution is given in a table. If the path length is 1 cm, calculate epsilon in meters squared per mole. So for this question, we need to use Beer-Lambert's law, which is this, which is A equals epsilon times L times C, with C the concentration being in moles per meters cubed and the length being in meters. So the conversion for molar to moles per meters cubed is just times by 1,000. So to rearrange to get epsilon is A over L times C. So for the first solution, the equation would look like this. 0.022 divided by 0.01, which is the length in meters, times by 10, which is a concentration in moles per meters cubed. That gives us an answer of 2.2. For solution 2, we do the same thing. 0.43 over 0.01 times 20, which again is the concentration in moles per meters cubed, gives us 2.15. Solution 3, we get an answer of 2.2 again, and solution 4, we get an answer of 2.23. Part D. The infrared spectrum of a compound X includes a strong peak at 1640 wave numbers due to the C double bond O in the molecule. Assuming that this is carbon 12 double bonded to carbon 16, calculate the reduced mass in grams per mole. So to do this, we need the equation. So M1 times M2 over M1 plus M2, and that equals the reduced mass. So for carbon 12 and oxygen 16, it would be 12 times 16 over 12 plus 16, which equals 6.86 grams per mole. So now we want to calculate the frequency of the signal. So we need the equation frequency equals C over lambda, which is the speed of light over wave number, and 1 over lambda equals the wave number. So if we put those two equations together, we get frequency of the speed of light times the wave number. So frequency equals 2.997 times 10 to the 8 times 1640 equals 4.92 times 10 to the 13. So for the same question, hence find the force constant of the bond. So the equation for the force constant K equals frequency equals 1 over 2 pi times K over mu to the power of 0.5. So first we need to do the reduced mass, and we need to make the units kilograms per bond. So we divide 6.86 by 6.022 times 10 to the 23 to get 1.13 times 10 to the minus 23 grams per bond, and then we divide again by 1,000 to get 1.13 times 10 to the minus 26 kilograms per bond. So if we sub in all our numbers that we've just worked out, we have 4.92 times 10 to the 13 equals 1 over 2 pi times K over 1.13 times 10 to the minus 26 to the power of 0.5. So if we divide by 1 over 2 pi, we get 3.088 times 10 to the 14 equals K over 1.13 times 10 to the minus 26 to the power of 0.5. So then we have to square each side to get rid of the 0.5, which gives us 9.537 times 10 to the 28 equals K over 1.13 times 10 to the minus 26. So then we times each side by 1.13 times 10 to the minus 26, which gives us a value of K of 1077.7. If we move to done the calculation for the carbon 13 to the oxygen 13 bond, what would not change in the calculation other than the equation and the value of pi? Force constant wouldn't change.